I hope everyone's okay. I just got about partway through this paper. This is the Edexcel AS paper, which is on Friday, and I thought that the feed wasn't very good, so I've stopped, and I'm starting again here from the open response stuff. So the previous video on my channel will be the multiple choice ones. I'm going to go through from here. Okay, if it's not doing very well live, then hopefully they'll be there. Hopefully the multiple choice will be there later on tonight. This is the Edexcel 2016 AS Physics Paper 2. So here we go, we're on question 9 and we're talking about optical fibres now. Okay, the optical fibres use total internal reflection. So you can actually just remember the good old equation that the refractive index is equal to 1 over sine of the critical angle, if you like. But what you need to know about the equation as you get given it in the formula sheet is this is Snell's law, and actually at the critical angle then the sine of the outside angle is 90, so at the critical angle it's refracted along the boundary, so that's where that 1 comes from. So here we go, we just need to make sure we put things in the right place here. We want to know the critical angle, which is the angle inside the first medium, and we want to know, and we know the refractive index of the first medium, the core, and we know the refractive index of the second medium, which is this one, the cladding. Okay, so we just plug in those numbers where they go, sine of 90 being it's refracted along the boundary. So we rearrange for C, and it gives us sine to minus 1, 1.2 over 1.56, 50.3, and that's 50 degrees, roughly 50 degrees. Now these show that questions, a lot of people don't really know this, but it means that your answer, the final answer you get, is going to round to the show that figure. Okay, can you just give us a thumbs up if the feed is looking good now? Because I'm about halfway through this paper. I started and I did the multiple choice, and the feed wasn't very good. So I think that I've stopped, and hopefully the feed's looking good now. I'll get to any comments or any questions that you've got later on, but this is going to be just a really quick run through of an AS paper 2, which is on Friday. All right, I'm going to crack on through then. Okay, so this one then is solving what happens to this kind of beam of light. Now the beam of light is that entire section between 60 degrees and 30 degrees there. So in other words, this diverging beam here, right? So the three students have made these suggestions. You have to figure out which one's correct. Now you've just worked out the critical angle, or they've given you it, and if they give you a figure as a show that, they're expecting you to use it later on. So you have to think to yourself, well, some of this beam is hitting the cladding, the boundary, at greater than the critical angle. And remember, guys and girls, that the critical angle is between a normal and the ray. So it's actually this one which is going to do the TIR, the total internal reflection. So this one is going to be refracted, and this is the path of that, and this is the path of that. Now it says, state which student is correct, adding to the diagram to illustrate your answer. So I get a mark for this ray, and a mark for the TIR ray, and I get a mark for stating, therefore, that student C is correct. I hope that makes sense. The key is in this bit, some of the beam. Okay, so that beam is actually wide. It's one of the reasons why we can't do these practicals accurately, because we can't really get single narrow beams. Okay. So this one, straight away you can see a stress equals strain graph. So you're going to go to the Young modulus part of your equation sheet, and you're asked to calculate the force. Here's the way I do questions. I always underline the command word. Okay, so at a strain of 0.02. So actually the first mark is just for accurately interpolating from the graph. So 0.02 up to the line and across to this. And I've got a lot of people doing this wrong for a couple of reasons. They're not doing this very accurately, or they're thinking that that line must be 50 as that's 40. So they come up with something like 48. So it's 56 megapascals. Okay, then the equation for stress is force over an area. That's from the equation sheet. Rearrange for force and sub in the numbers, not forgetting the standard form for megas times 10 to the 6, and the standard form that you're given there is 10 to the minus 6. And you end up with 67.2 newtons, or just 67 because you've only been given 2 sig figs. Okay, the next one, determine the extension of the stroke at a strain of 0.04. So strain doesn't have dimensions, doesn't have units, so you don't need to worry about that. Again, you get the equation from the formula sheet. Strain is equal to extension over original length. You're going to turn the original length into meters, even though you don't really need to, because you would just get an extension in centimeters, but that's good practice anyway. And then you rearrange for extension. Okay, strain times the original length gives you 0.01 meters. Okay, and that's the final answer. Then you're asked to deduce whether silk or polythene is better for making the waste bags, and you need to apply what you know about the stress strain graphs. Okay, the gradient is steeper for the silk, so it's stiffer. So therefore, to get marked for saying it's stiffer, the silk doesn't stretch as much. Okay, that's a better thing. So we're going to use silk. And also silk has a higher breaking stress, so it is stronger. So you probably would sum that up by saying silk is the better material, more suitable material. Okay, next one. I'm hoping this is okay. I'm hoping this is looking okay. Just streaming off my 4G. Okay, let me know, please, if the quality of the feed isn't that good, and maybe I'll go through it again as a saved video at some point. Okay, difficult one then. A dark shadow is seen on the screen behind a ball bearing, source of light ball bearing the screen, and there's a small spot of light in the middle. Okay. Firstly, use Huygens construction to explain the behaviour of light as it travels past the edge. Now, here's my suggestion to you. If you ever read that, use something, okay, bang down a definition of that thing first. So my first point is secondary wavelengths interfere to produce wavefronts. That is Huygens construction in a nutshell, basically. In other words, a wavefront is a point where everywhere along that wave you've got equal displacement from the equilibrium position. So what happens, why is that the light diffracts at the edge of the ball bearing. So the light diffracts from this edge, and you get this interference pattern on the screen. Or in other words, you get this bright dot right in the middle of the ball bearing. Why is it right in the middle? Okay, explain why it's right in the middle. Well, that's because the diffraction from either side means that you get an equal path difference to the middle of the screen. Okay, so the path difference to the center is 0. So waves are in phase, so constructive interference occurs. So if you ever know you're doing standing waves of any form, then get this type of things in here. Phase difference, constructive interference, that level of detail. Okay. Next one, state the model for the behavior of light in this experiment demonstrated and explain why the scientific community accepted this model. So this is not really about waves at all, actually. Well, you do need to know it's the wave model, fair enough, but actually it's about models and why we accept them or change them. So we accept them because we can see evidence from experiment and they're reproducible, okay? So we do experiments, and if we get the same bits of evidence over and over again, we get the same findings over and over again, we accept that new model. Okay, there are other things you could have said, okay, it's supported by previous evidence, or that this demonstration could be repeated by others. So there are a few ways to get this kind of mark, but I think that's the most kind of obvious one. Next one, the ball bearing shown in the experiment has a diameter of about 1 centimetre. So describe how the diameter can be measured accurately. So when they're talking about this, they're looking for a correct instrument. A micrometer is okay for accurate measurements of things around 1 centimetre to about 5 centimetres, no bigger than that. Okay, and what you must say with any diameter or any kind of micrometer measurement, you do several readings in different places and calculate a mean. You must say both of those things for this mark. You must have several readings in different places and a mean for this kind of mark. So that's one of your key kind of improvements to practicals. You take a mean, and but you do the measurement in different places across different diameters. Okay, moving on. This one is about an experiment on a guitar string. You should know this. This is a core practical. Make sure you've got absolute detail learned for those core practicals that are coming up in this exam on Friday. She investigates the effects of varying the tension on the guitar string and the sound produced when the string is plucked. Describe a method of varying the tension in the string. So you could just use pulley and slotted masses hanging from the end of the sling, okay? And then the tension is just the weight of the slotted masses, or in other words, mg. So if you just said T equals mg, you'd actually got this mark. Okay, that should be a really easy one if you've memorised enough detail from the core practicals that you've done so far in year 12. Okay, the student records the following data and plots a graph. Complete the table and the graph. So the first thing is you should notice that's just frequency squared, so that should be an easy mark, absolutely easy mark. Then you have to complete the graph. So the next thing to do is plot the missing point. That was that one. Remember, when you're plotting, you have to plot to half a small square accuracy when you're plotting and when you're reading from graphs when you're doing gradients, okay? Always half a small square accuracy, so that was that point there. And then what would the graph be missing? A lot of people seem to have missed this off in my group. It's missing a line of best fit. So completing the graph means put a line of best fit on. Now it actually goes through 0 in this case because we know that this practical has a straight line through the origin. Here's quite a tricky one. Okay, where you actually have to determine whether the guitar string using the experiment lies within this range. So this practical is all about measuring mu, which is the mass per unit length of any string. Okay, so firstly you go ahead and you get the equations that are relevant. Okay, the equation that's relevant is this one here. Wave speed equals the root of the tension over the mass per unit length. Now, a lot of people get muddled up here because capital T is also used for time period. In this case, in this experiment, it is tension. You also need to use this one though here, in that you're given a length of the vibrating string, and you should be able to convert that length because the strings vibrate in their first harmonic, their fundamental frequency, if you like, as half a wavelength. Okay, so that 0.4 is the length of the string, which is half the full wavelength. So the wavelength is 0.8. And actually, just doing that gets you a mark. Okay, now that V is equal to F lambda, so you make them equal. And remember, frequency was on the graph, wavelength you've just been given, so you know these things, so you can do the analysis. And then I've just gone and rearranged, so square both sides. Rearrange for F squared, because you can see that is the y-axis of the graph. So here's another really important skill, is equating the algebra to y equals mx plus c, or in this case where it's going through the origin, so there is no c. So I've made my equation look like a y equals mx model. Or in other words, I'm saying the gradient of that graph is going to be 1 over mass per unit length times the wavelength squared. And then it's just a matter of going ahead and getting the gradient from the graph. Okay, you can all do that. Do it, as I said, accurate to half a small square. This bit I've also haven't mentioned that you have to equate this v to this v, and that gets you a mark. So that was a nice easy mark to get if you've learnt your core practicals. That's the gradient there. Okay, so you get a mark for calculating the gradient. Plugging the gradient into the formula, okay, and rearranging for mu is the final mark. Okay, so something in the range of 6.0 to 6.2 times 10 to the minus 3 kilograms per meter is the final mark there. And you need to, when you're given these questions in these new form of exams, you need to give a concluding statement. So yes, this number is smaller than the number I've calculated, which is in terms smaller than the upper bound of that range. So yes, it does lie within the range, is a conclusion for that. Okay. So we're plodding on number 13 now, okay, and if you've got any questions, if I've gone too fast for them, then do ask them and I'll get to them at the end. I'll just flip through any comments at the end. I hope this is going to be useful for you. I hope this is being useful for you. This one, you can see it's got the asterisks. It's a quality of written communication one, or a leveled response question. Okay, so they're going to be looking for important things for you to think about at A-level, is linking the points. So what I'd always suggest is do a little plan before you start this long written one, okay? Discuss the conclusions that can be drawn from the information about the behavior of electrons and the structure of graphite. So look out for the word and, talk about the behavior of electrons first and the structure of the graphite second, okay? You might want to expand on that, okay? Maybe think about the behavior of the electrons. This is the wave-particle duality bit, okay? So they're actually behaving like waves at this point. And you might want to think about, well, okay, the structure of the graphite, there's little gaps in between particles in the graphite, and you get diffraction there, okay? So here's the kind of conclusions. I've not bullet pointed it out, as you'll see in the mark scheme. I've tried to link it through. I've tried to write it as sentences, think about your connections. It doesn't need to be beautiful prose, it just needs to be well linked. So you need to say this means to this, and then this means to this, okay? So have a little think about that. So we can conclude that this is an interference pattern, and you straight away get the mark for just saying interference pattern. And interference is a wave behavior, so really we're concluding the electrons are behaving like waves. And I've even gone ahead and done an electron point, because isn't that an amazing thing that electrons can behave like waves? We can also conclude that higher speeds gives a set of smaller circles produced. So this is the higher speed one, and you're told that in the bump here. Okay, figure 2, the speed of electrons is increased, and the resulting pattern is figure 2. So we can conclude that higher speeds give us smaller circles. Now that's what you can conclude, right? That is the evidence that you've got in front of you. Now what else do you know about that, about the behavior of electrons and the structure of the graphite, is what needs to come next. So for waves, the angle between maxima is given by n lambda equals d sine theta. So as we've seen theta decrease, that's the angle between the kind of maxima in our diffraction pattern, theta's decreased here compared to here, then we know that lambda must have decreased as well. Okay, we're not going to talk about proportionality. Lambda is obviously proportional to sine theta, but theta decreases, therefore we know that lambda has decreased. Okay, The wavelength of an electron is given by lambda equals h over p, where h is Planck's constant, so that's a constant, and p is the momentum. So it follows that higher momentum means a smaller de Broglie wavelength. We call this equation the de Broglie wavelength equation. As we're getting these diffraction patterns, it means that graphite has a regular layered structure with small equal gaps between layers. And you could have said kind of any of that. You could have said a regular layered structure or small equal gaps between layers, okay? So what's actually happening is the diffraction is happening between the layers, and the amount of diffraction depends on the relative size of the wavelength and the gap size, okay? I hope that makes sense. That's a kind of 6-mark example answer, but there are loads of ways you can get that. Okay, this one was pretty tricky. I think people looking at this diagram are thinking, what on earth is going on here? So this is an electron beam can be used to explore the structure of solid materials. Diagram shows how an electron beam, here it is, reflected by the top 2 layers of atoms in the material. The 2 layers are separated by a distance d. So this distance between the layers is d. And remember that is distance d there. Okay. As I said, this is pretty opaque, actually, how you get to this answer. But let's have a little think about what we've just drawn there. So you're told this angle here. Okay, you're not told anything about any angles in here, but if you think about the extra length that this second wave has gone, this second beam of electrons actually, this second beam has gone as compared to the first one, okay, you can see that that is kind of part of a right angle triangle. And actually this angle theta is this angle theta in a right angle triangle. So this actually is just the opposite side in a right triangle. Okay, now you're asked to show the extra distance travelled, which is this distance, and the same distance on the other side, is equal to 2 d sine theta. Okay, so essentially this distance here is d sine theta in a right angle triangle. So you just have to kind of put that into words, or you can sketch a little thing and you can add to the diagram, okay, to make it clear. But try and make it clear to the examiner 2 things. Basically, try and make it clear that you recognise that there is the angle theta is this angle in a right triangle, okay, and therefore the extra length on that right angle triangle is d sine theta. Okay, so you can do that, that's just trig. And then the extra length is before and after the reflection, so the total length is given by 2 d sine theta. So you have to make it clear to the examiner that there's an extra length is repeated twice, okay. Next bit, one reason why there's more than one ring shown in figure 1 and figure 2. So this is figure 2, okay? No, these are figure 2s, aren't they? So the figure 1 and figure 2 is the 2 diffraction patterns that we've seen, okay? Here, why is there more than one ring? Well, what we call them is these orders of maxima, okay? So really all you have to say is there's more than one order of diffraction in the pattern. Okay, that actually will get you the mark. They're just looking for more than one order. But I think I want to explain that to you guys, and you might want to explain it to the examiner, i.e. each ring corresponds to a multiple of the path difference lambda. Okay, so in other words, you could have another beam coming in and reflecting off this layer, okay, and that would cause 4 sine theta, I guess, and therefore you'd have another order on the end of your diffraction pattern. So 14, these are pretty tricky, these thin lens stuff in the new syllabus, okay? There's loads of detail on here, okay, and it kind of confuses people. Really read things and try and figure out what's going on before you kind of look at the questions. Okay, this is the objective lens, this is the eyepiece lens, okay? So there's actually, in a telescope, you've got the objective and the eyepiece, and they're working together. And so the distant object, okay, these rays are coming in here, kind of parallel to each other. They're being refracted by the lens, and they're making an image just here at P. Okay, that image at P is then going to the eyepiece. Okay, now the eyepiece is again going to do some refraction, and that's going to come into our eyes, and we're going to observe that as if it's coming from the image where Q is. So there's actually 2 lenses working together to make a magnified image. Okay, but the first question is pretty simple. Okay, you didn't really need to know any of that, understand any of that to get this right. You just needed to know that the power of the lens is 0.820, and that the focal length and the power are related by, they're related inversely. So the focal length of the objective lens is 1,200 millimeters. Okay, so you just need to basically invert that. So you just plug P into the equation there, and you get this. Diopters gives you meters, but then so you just need to state that that is equal to that many millimeters. And again, what you calculate should round to the show that value. But the show that value is going to be used later on. So explain why the image of the moon produced at P by the objective lens will be at a distance of about 1,200 millimeters from this lens. You're told that's the focal length. So why would it be at the focal length? Well, essentially, it's because U is very large. Now, U is the distance between the object and the lens. So actually, the distance U is huge in this case, isn't it? Okay, so really, if we think about that distance U in the thin lens equation, then this means that basically 1 over f is approximately equal to 1 over v, and v is the distance from the lens to the image. Okay, hopefully some of this is making you clear on what bits you need to work on for in the next day or so, to make sure you can do them in the exam. And I think this is a bit that people are struggling with because it's new stuff in the new syllabus. Okay, so moving on. So basically, v is roughly f. You're told f is this before, so in other words, that's why. Okay, next one. There's been a few questions, and I'll get to questions just towards the end if that's okay, to stop me kind of the flow, especially for people who are watching this back afterwards, and I imagine there will be a few people doing that. So state the properties of the image at P. There's only 2 marks, so you have to get all 3 right for the 2 marks. The image at P is real, it's diminished, and it's inverted. So that's just reading the diagram here. It's real because it's made by real rays. Okay, or if we put a screen there, it would be projected onto it. It's diminished, it's smaller than the moon, and it's inverted, it's upside down. Okay, then it's pretty tricky, so you need also all 3 of those to get the marks. The eyepiece is at a distance 100 millimeters from the image at P. Now, in this second kind of step of the telescope, the image at P becomes the object. Okay, so you need to think about that. So I've actually drawn it out here. So that's the image P, and you would actually get a magnifying glass effect. Okay, so this would be the new image, that's the object, this is the image. Okay, and you'd get this thing where the rays would go in there, but even though it needs to be a converging lens for the magnifying glass effect, they diverge because we're closer in than the focal length of the lens. So you need to decide which focal length to use. And again, it's using the thin lens equation. Now remember this, when the image is projected in the wrong direction, if you like, it's the same side as the lens as the object was, then you have a negative V. So V is minus 300, okay? So I've put 300 is minus V here. And then you use the thin lens equation again. It's all right, buddy. And you use the thin lens equation again, but make sure you've got the negative in there. And you'll find that 1 over f, just by banging all this into the calculator, gives you an f of 150 millimeters. Okay, and again, use a concluding statement. Okay, when we're asked to deduce something, when we're asked to comment on something, always use a calculation and do a concluding statement. Okay, now it's section B, and I hope you're aware of this. Section B is going to be like the general and practical principles of physics, so exam in A level. So you're going to be asked questions on just any part of the syllabus, so you need to actually bring all of your things. This is the synoptic ones, bringing together different elements of the syllabus all together in one thing. Okay, so read the extract and answer the questions that follow. Now actually, you read all this extract and your mind's blown because you've been told about some powdery dust on the moon, and you're like, where am I supposed to get anything from that? Okay, but the point is, well, ultraviolet radiation knocks electrons off the atoms of the lunar soil, and then it's asked you to describe the particle model of ultraviolet radiation that explains how it can knock electrons out of atoms. So actually, you just need to recognize this is a quantum question, particle model, and they've asked you to describe ionization. So this question really says, describe ionization. So you don't really you need to kind of decode that to the simple statement that you can probably do if you understand your quantum, whereby photons come in and give electrons energy, and so they're released as photoelectrons. So let's look through the 3 possible marks. So you just needed to state that the UV was photons, okay, wave particles of light, something like that, packets of waves, something like that. Individual photons interact with individual electrons. It's a really key point from quantum. Always be imagining an individual photon interacting with an individual electron. And if it's actually stating that, gives you a mark sometimes, as does stating that the energy of a photon is given by E equals HF. Okay, so that actually could have been your second mark as well. But you needed to state that if the frequency of UV is large enough so that HF is bigger than the work function, phi, the electron is released as a photoelectron. So that is the point we're really looking for. The UV photon has to have a large enough energy such that it's bigger than the energy, like binding the electron into the atom, or bigger than the energy difference from wherever the electron is up to the valence band and beyond. Okay, so if the electron is here at this energy level, then you need, this is the work function between here and here, and you need HF to be greater than the work function. Okay, and then you'll have some kinetic energy as well. So this is all in Einstein's photoelectric equation, which is energy in the photon is equal to the work function plus the maximum kinetic energy of the photoelectrons observed. This is the little experiment, and I do have a video about this experiment, so go and check that out afterwards if you're not sure how to do this. Okay, it's not one that you're likely to have done because it's quite specialised, but it is pretty cool once you get it done. It's actually not really about that experiment at all. It's explaining how a potential divider circuit can produce a range of values from. So you don't even need this. Okay, you just need to explain what a potential divider is. So potential dividers allow us to share supply PD in the ratio of two resistances either side of the connector. And I've made it clear what I know what the connector is just by drawing a little arrow there for the examiner. So in other words, if you move this connector down here, then there's zero resistance in the circuit. Okay, so the ratio is 1.5 to 0, and you've got zero resistance in the circuit, so the supplied PD to the circuit is 0. Move it to the other end, move it to the top, and you've got a maximum resistance in the circuit, and so the supplied resistance is 1.5. So isn't that good? That looks complicated, but you didn't really need to understand that. You need to understand potential dividers. So here we go. The potential difference on the voltmeter is increased until the ammeter reading is 0. So this means that the potential difference is what we call V stop, okay? The stopping voltage. And the stopping voltage is like applying an opposite kind of energy to the charge than the kinetic energy that the charge had. So this was the kinetic energy the charge had, and we've stopped it with this voltage. So we've essentially measured that kinetic energy by stopping those charged particles from getting across that gap. So a maximum kinetic energy is just 0.6, the voltage, times by the charge on an electron. So the formula, the unit EV is like a formula for the energy. So you didn't need to convert to joules. A lot of people try to do that. You actually just need to recognise that 0.6 volts corresponds to a maximum kinetic energy of 0.6 electron volts. All right, here's a tricky one, and I wouldn't really expect an awful lot of marks to be scored on this because this is where you really did need to understand the bump that they're talking about. Okay, but discuss whether the photocell arrangement in part B gives a valid demonstration of how dust particles become charged on the moon. Right, they're valid as both are conducted in a vacuum. So just try your best to think about what are the similarities and differences between the two situations, really. So valid comparison means that, well, valid demonstration means that the situations are similar to each other. So yeah, there's a vacuum on the moon, there's a vacuum in the photocell. Both theory on the moon and the demo both use the photoelectric effect. So it's not like we're trying to demonstrate something that's got a different theory about it. Okay, they're both actually the photoelectric effect. So that's what you need to put in there. There's two things for valid. It's not valid though because the moon isn't the same material, it's not a metal. And there are different wavelengths of light use. So UV light on the moon, visible light in the lab. There are some other things you could have said as well. You could have said that the dust is free to move, but the metal plate is fixed. Fair enough. You could have mentioned that the UV removes electrons from individual atoms, but in the demo, the light removes electrons from the metal's surface. Again, doesn't make much sense to me, but it's not what I would have written, I'm sure. The demonstration is based on the photoelectric effect, but the moon could be other forms of ionization. So it could be ionization by ionizing radiation, because the moon isn't shielded by an atmosphere. Okay, so there are other things you could have said. Tricky one, try and think about why it's like it, why it's not like it, why is it valid or why it's invalid. Last question on this, okay, again, look, this is a Unit 1 kind of idea, it's mechanics, but it's in a paper 2, so make sure that you're sure about all of your AS physics before you go into paper 2, because you're going to be asked to rely on all of it. Okay, so firstly, complete a Freebody diagram to represent the forces acting on the climber. Just ignore the little line I've drawn there, there's the free forces. Okay, the tension in the rope at the angle 20 degrees. The vertical, you didn't need the angle for that, but you need to write tension. The weight of the guy is always straight down. Oh, I've said guy, it's a she. Need to get out of that habit, but the reaction is the force that the rock does on her because she's pushing on the rock. There are the three forces. Okay, you can always, if you ask for a free body diagram, make sure you put a weight on straight away, get yourself a mark. Think about any third law pairs producing reactions. We don't need to put her force on the rock because this is just the forces on her and the tension in the rope. Okay, now actually they would make a closed triangle. So the next question asks you to show the tension in the rope is about 600 newtons. Remember, so we're looking for an answer that rounds to 600, okay? So you've just got to think about it like this. Well, the weight is equal to the vertical component of the tension. So you've been given some other information to do this, 20 degrees there. So you can essentially just draw yourself a triangle whereby the weight, look, is equal to the vertical component of the tension, T. Then just write yourself a little expression for this side of the triangle using your trig functions. I always think about it like this. Well, if I've got the tension there and I want to get this side, I have to close the angle. So W equals T cos for close 20. If I had to swing the angle open to get this one here, which would be R, then that would be sine. Okay, but I'm not bother using that. And there we go. Convert. We've given her mass right at the very top, 55, 9.81 mg over cos 20 gives me, there we go, 574. Anything that rounds to 570 is given the mark in this case. So where are the marks then? The marks for making a trig expression and the mark for using mg essentially. Okay. Last two bits then, calculate the energy stored in the rope. So go ahead and get the equation from your formula sheet. This is the equation for elastic strain energy is a half F delta X. Okay, and make sure that you're using the force that you calculate as mg. Okay, let's just sub in the numbers in with the centimeters converted into meters for delta X. That's the number you've got to calculator. That would be good enough for the mark. I've given it to 2 sig figs because that's all they've given me. Lastly, one assumption we've made in this calculator is that the force is proportional to extension. In other words, it obeys Hooke's law. All right, I hope that was helpful. That was a really quick run through of a second paper, okay? I've obviously solved the things. Use this as a little resource for your revision, is what I suggest. You've got another day, another evening to do this. And go ahead and go through this paper, go through this video, make sure you just skip past any bits that you got really easily and go over a couple of times the bits that you weren't sure about. When you find the skills that you couldn't do, you didn't understand what I was chatting about, then stop and do that little bit of revision. Make sure you can do it and you'll be fine. You'll be able to do it in the real thing, okay? Remember, all of these things behind me, all these equations and all these ideas, they're just sets of rules that you can use to solve the problems in front of you. So think about the problem, identify the tools to solve it, and go ahead and do it. Right, hopefully I'll see you. Oh no, I was just going to check if there are any comments. Not very many, okay. How different are the physics courses? Not very different at all. Year 13 taking OCR B and wondering if it's worth watching videos on papers like this from other exam boards. Yes, it definitely is. If you think about what I've just said that these are tools to solve problems. Okay, so every single physics board has the similar kind of problems to be solved and the same set of rules. Physics doesn't change between the different boards. It's just the same set of rules to solve the problems. All right, I really hope that helped. Let me know if it did or if it didn't. If you'd like to see more videos like this, then let me know that as well. Okay, it was really quick, lots of energy, but I hope it was useful and see you soon.